We're ready. Let's get going. Sorry for all the delay there getting set up. It has been somewhat chaotic, but let's kick off anyway. My name is Stig Telfer. I am CTO of a very new and very exciting Bristol-based startup, OSDUK16. I think following on from Cray is a big act to follow, and we are a small act, so do bear with us. But I think with slightly less ambition, perhaps we also we have a slightly different kind of achievement from that ambition. But before we go too far, I can guess what is in everyone's minds right now. This is the tail end slot of the day. It's been a long day. It's been a good day. But who is this guy keeping us all from the beer? Anyone who's out from out of town, I should warn you, don't come between a Bristolian and the bar. It's like a hippo and the watering hole. I have a theory about Bristol beer. You should watch out for it. It emits a gas. It's like an isotope of helium, Bristolium perhaps. It makes your voice ever so slightly West Country, so be aware of that later. But okay, let's get started with a little bit about me, a bit of context and background. Firstly, this is great. I'm really, really pleased and really excited that we are doing this event here in Bristol. Bristol is a great tech city. I first came here in 1992 as a student working at Mako, the parallel computer pioneers. Some of the source code from that time was recently found in the back of Wookiee Hole. It's that old. But since then, I mean, it was a fantastic foundation for everything that has followed on since then. It really was a great grounding for me. I followed on from Mako working on the DEC Alpha in the United States. Then I had one of my favorite projects of my career, which was, well, you might describe it as an industrial machine vision application with real-time neural network image analysis, various generations, dual alphas, 24 Tiger Shark DSPs, 3 FPGAs, and then GPUs. But it was also a machine for identifying the visual qualities of potatoes. So here are some potatoes from earlier. They look very tasty, but if you look at them, how would you use a video camera to work out that those are good potatoes? How do you spot that the eyes on a potato, the little bits of soil, the little bits of scurfy stuff, yeah, that's all fine. But what about the stuff, you know, the black festering mold and so on? You need serious compute power, it turns out, in order to identify the good from the bad. And that's what we're working on. It was the most fascinating and fantastic project. Happy times. Those guys have moved on. I parted company with them with the birth of my daughter in 2007. They've since moved on, and last I heard, they were turning carbonized potatoes into graphene. So plenty to be done there, I am sure. So then I moved on a bit. I'll speed up if I can. I was working with another Bristol legendary firm, Quadrix, doing HPC network interconnects. I was doing some work with them, working on site with some of the big supercomputer deployments that they were putting together. So this was a sort of 1,000+ nodes in the time before DevOps, which perhaps to some people sounds like the time before time itself. It was a fascinating challenge. It really wasn't that bad. Really interesting experience. Then I moved from Quadrix to Bristol-based startup Nodal. We worked on software-defined network Ethernet fabrics. We built our own Ethernet chips. And we were creating fabrics which looked a little bit like this. That is a computer network. It's an Ethernet network. But in the words of one of the co-founders of Nodal, it's probably not your dad's Ethernet. But that's the kind of concepts that we're creating, these multi-path congestion managing Ethernet systems. So then I spent a couple of years working with the Cray Bristol team. It's really good to see you guys again. These guys are leading the company's R&D efforts into OpenStack, and I think they're doing a fantastic job of it as well. So, but then I jumped. I took a big leap, and I went to become the CTO of OSDUK16. This photo on the screen is me shortly after becoming CTO. You don't have to do this to become the CTO, but I kind of did it anyway. The pillars, actually, if anyone knows it, it's Adam and Eve on the top of Tryfan in Snowdonia. It's a fantastic place to go. I would say that, have you ever heard of disco leg? If you can imagine what disco leg is, that's what I had after doing this. My legs were wobbling like crazy. So this is me really exploring my love of visual metaphors for career changes. And I shared this with John, my co-founder at Stack HPC, but he didn't think it was quite so. He thought that actually the pill on the left looked far too substantial, really, for the metaphor to hold. So, well, anyway, let's move on. So what are we doing, and what was the point of creating this company, Stack HPC? We are formed out of a group with Cambridge University, who I'll get onto in a bit. It is about exploring this new driving force in HPC, which is OpenStack. So OpenStack is really taking cluster management and research computing, academic and scientific computing by storm. It is a huge success in this market, and we're going to talk a little bit about why that is today. Everything is changing very fast in this space, so the notable thing about OpenStack really is just how fast it evolves. I mean, when you look at sort of the conventional ways that you might manage an HPC cluster or any sort of large piece of compute infrastructure, OpenStack is just outrunning and outgunning the whole lot. I mean, it doesn't do everything that those things do, but it is changing and is growing so quickly, new capabilities all the time. Some of the information in this presentation is only a few weeks old, so if your opinion was formed before that, it's already getting a little bit out of date. So our mission really is about bringing people together. So we work with the OpenStack community and the research computing community to really bring together the users of OpenStack in research computing contexts and to enable people with HPC configurations to share the information about what best practice is, what really works, what problems they've got, what things to avoid. And then finally, we're looking at developing new HPC capabilities and bringing those into an OpenStack ecosystem. So I think that's probably enough of that. A little example, a little taster of this. That's a nice picture. This is a supercomputer, or is it a cloud? So this is a machine called Bridges. It's at Pittsburgh Supercomputer Center. It's got about 900 compute nodes. It came online early this year, depending on when you consider coming online to be. The little red squares at the bottom are the compute nodes. The green ones are equipped with quad GPUs. The networking for the rest of the diagram is OmniPath, 100 gig. And the nodes at the top are all the special services that this machine provides. So a lot of those nodes have very high memory, a few with 12 terabytes of RAM. This machine has petabytes and petabytes of parallel file system. It just sounds like a supercomputer, but it runs OpenStack Liberty. It runs RDO, it runs Puppet, it's bare metal, compute is managed by Ironic. So it's a cloud. It's a bit of both. And this is really the embodiment of the kind of systems that can be created today using OpenStack for HPC infrastructure management. So on to what we're doing at Cambridge. Cambridge, I mean, it really doesn't need any introduction, but Cambridge is a major player in global scientific research. The annual R&D budget across the university is £370 million. And obviously, the budget doesn't really factor in all the academic work that's going on as well, aside from R&D. 500 papers are generated using the research computing facilities at Cambridge every year. Research computing supports 197 research groups in the university, 42 departments, and research computing runs several supercomputer class systems, some really big systems. Each of them, though, is kind of special, and it's kind of dedicated to supporting a different environment, different workload context. You've got your classic sort of conventional HPC, things like Slurm for workload management, MPI, InfiniBand, high-speed message passing, tightly coupled workloads. We also have a very large system for performing GPU-intensive calculation. We have several big systems for performing Hadoop and Spark workloads. In one data center, we have 5 petabytes of Lustre file systems alone. The image here is actually none of those. This is an image from the Square Kilometre Array, which is a flagship research program is going to be absolutely massive. Really, they're just in sort of iterations of the planning phases. These are radio telescopes from what do they call a pathfinder. This is just like a test case prototype in the desert in South Africa. Cambridge is the project lead for the compute engine that is the core of this system. It's 450 petaflops estimated, which is God knows how much, 9 or 10 times bigger than the biggest machine you can get out there today. This needs to be delivered in 5 or 6 years' time. So the research that is ongoing now is really about building pathways to delivering that system. Cambridge is the project lead. The project I'm working on, and the one I'm going to talk about today, is nothing to do with radio astronomy. This is one about life sciences. So this was a new project in 2016 for bioinformatics. It's really an interesting project because it's a hybrid of HPC and OpenStack. It's got a giant amount of storage attached to it. This is our case study for today. The system uses OpenStack to support the really diverse research activities in bioinformatics. Bioinformatics is a really broad field. It's what you might call non-traditional HPC, or the long tail, people sometimes call it. But also there's a lot of work which is actually going to be interesting. It's going to be conventional, it's going to be MPI, it's going to be Slurm and workload managers. So what we've created is a system which can do both, and anything else that we ask of it as well. These images on the slide, they're brain scans from one of the early users of the system, which is the Wolfson Brain Imaging Centre in Cambridge. I chose these scans. These are actually scans of an OpenStack sysadmin who is debugging Neutron. And it might look like false color, but I can assure you that is real fire. Very important when you see one of these sysadmins and they're in the middle of some networking troubleshooting, not to interrupt them, because particularly if you get to the stage where the smoke is coming out of the ears. So be aware of that. So you can see that Cambridge is already making many contributions to the community, to the OpenStack community, some of them slightly less fictitious than that one. So we have a big project, and the university brought together a large number of vendors from across both HPC and cloud ecosystems, some from both. Obviously, there are people who span both worlds, like Red Hat, Mellanox, and Dell along the bottom there. But the system that we have specified and put together is based on Red Hat OSP. We're using OSP8, and we are in the process of moving to OSP9. The system uses Mellanox Ethernet, so we have a mixture of 50 gig network to the nodes and 100 gig network to the network fabric across the core of the system. This is what a hardware engineer would not really call a system diagram, but for a software engineer it probably suffices. So that's what I've gone with. There's 80 compute nodes. They're modern, good Dell kit. Obviously not a hardware person's appraisal of them either. They're 48 CPU cores, 128 gigs of RAM, and then we have 3 controller nodes in an HA configuration for running OpenStack. We also have a number of different vendors and a number of different platforms for storage in this system. So we have, one of the interesting ones is we have 2 NextCenter products. We have NextCenter Edge and NextCenter Store. There are 3 petabytes of storage managed by the NextCenter systems. We have a slightly smaller Ceph storage, and we have Lustre storage coming in from across the data center. Actually, there's 2 data centers involved here. We have a second site, which is for, in some senses, for HA. This is the system that we are building today. So what's special about this? Well, nothing so far, really, but I guess that the underlying concept of this machine was this idea of an RDMA-centric OpenStack cloud, an OpenStack cloud for HPC. RDMA, if you don't know, is this idea of remote direct memory access. So it's this idea that you can, from one system, send data across the network and into the memory space of a reuser process that wants to receive it at the far side, completely bypassing all the kernel networking stacks. It's fast, it's CPU efficient, it's low latency, it's brittle, it's fragile, it's all many other horrible things, but it also delivers very good performance. So that is the driving factor of this cloud. Can we actually create a cloud which has RDMA networking supported all the way through its core? We don't want to throw the baby out with the bathwater, though. At the same time as having HPC-style networking, we want to have cloud-style software-defined networking. We want to have the two of them working together in the same cloud system. So given that brief, everything else, every other design decision has flowed around that requirement. And it's made some interesting contortions in the design. You might think we'd tick all the best and whizziest things, but actually in some cases you can't do that because it would conflict with this requirement for RDMA networking at the core of the system. I don't know if you can see it, it's very blue and not very clear, but the Mellanox multipath fabric in the middle, it looks a little bit like that old nodal network, which I think is largely coincidental. It's actually not nearly as good as that was, if you don't mind my saying so, but that's a prince in the pauper's grave. The multipathing network here is layer 2, again because of the RDMA constraints that we started with. We do multipathing using multi-chassis lags between the switches. A layer 3 next generation network based on ECMP is imminent, but not there yet. So how do we actually go about this idea of bringing together these two stacks of networking technologies and actually making them talk to each other and work together? How do we build an RDMA-centric OpenStack cloud? So the first requirement, we need 3 network interfaces, which is what we have at the bottom of this diagram here. The system is deployed using Red Hat's OSP Director, OOO, to everyone who knows. And so that is all managed, and all the deployment of that is managed through the 1 gig NIC. All the imaging goes through the 1 gig NIC. When OOO starts up, it needs another NIC to talk back to the rest of the world and create the OpenStack control plane. We use a 10 gig NIC for that. And then for the application workload and all the data movement that's going on in our system, we use a 50 gig Ethernet NIC for that, which is where all the HPC networking technologies come in. So we fire up OOO and we install a bunch of Red Hat services, OpenStack services, sorry, and they in turn create a load of software bridges which go down onto the 10 gig control plane. We then create our network. So we create a couple of VLANs for our layer 2 network, which are for segregating away the tenant inter-VM communication traffic and the storage traffic, which is going into the hypervisor. We create VMs for isolating those so that we can apply separate QoS. We can apply different management policies for these different requirements for those different classes of traffic. So what's next? Then we start to install the HPC bits. So this is Open Fabrics, or OFED. This is the technology which enables us to bypass the kernel, ironically written in the kernel. And on that, we build a couple of HPC network protocols for data movement. So we have iSCSI over RDMA, and we have Excelio, which is the data mover for Ceph using RDMA. Next piece of technology is that we start to introduce some virtual functions. So virtual functions are little sort of virtual facsimiles of our high-performance NIC. Each of these can be looped into or passed through into a virtual machine, and then we get a much more efficient and lower latency, higher bandwidth network device, which is sitting directly in the VMs. So VMs come on then. There is our workload. Now, this is one of the other interesting design decisions that we have with the system. In order to support the high performance, we're using RDMA and SRIOV. SRIOV circumvents the operating system. So it circumvents all those things like security groups. Now, Cambridge is peppered with attacks all the time. They're very conscious of this. They're very aware. They're very proactive in policing these. So having an OpenStack system in which there is no inherent firewall is not good. So what we do is any externally accessible networks go through a VXLAN network mechanism, which is software controlled. It goes through the tenant network through the 50 gig NIC, but it is not as performant as the SRIOV, which is used for direct workload, internal east-west kind of communications. So then we pass through the SRIOV network interfaces into our VMs, and then we install OpenFabrics again inside the VM. And this time we run upon it, so a different set of protocols. We run things for Lustre client, high-performance file systems, and we run things for MPI, which is the message passing library for high-performance computing parallel workloads. And that is what the compute nodes more or less look like. The next stage, or the next thing we might look at is how do we actually go about deploying them? Now we know what a compute node looks like. We've got 80 of them. How do we go about deploying this whole system? So really the first thing that comes about is we need to start configuring the BIOSes and the baseboard management controllers on the system. We've just unpacked a load of boxes. We power up the BIOSes. We give them IP addresses. And then we need to make sure that all the configuration settings that we're using for things like VTD, IOMMU, all the important BIOS settings that we need, and all the RAID configuration is assigned. Now, there are difficult ways to do this, and there are nicer ways to do this. The way that we really like is using Ironic's DRAC client. These are Dell systems, so we talk to the DRAC. So we package up Ironic's Python DRAC client, and we put that into an Ansible module, and then the goal state in terms of BIOS configuration or RAID mapping or those kinds of things becomes YAML data files. These are templates. We run that over our BMCs. It then harmonizes the whole lot into one consistent state. This is something that we're working on. It's showing very good promise. We can do the RAID stuff. We're working on the BIOS stuff. I like it. The bear, by the way, is the Ironic bear. I love its attitude. It's got high levels of sass about it. Anyway, it's a good logo. So that usually works. The next stage in the deployment process is really to start to get those nodes registered with Ironic for bare metal management. So we go through the enrollment process. We upload a JSON file with a load of IPs for the BMCs, a load of MAC addresses, and that's all the information we have for now. Then we tell Ironic to power up the nodes. Ironic does this, gives them a special RAM disk, and then the RAM disk gathers all the other data. It gathers a whole load of data about the serial numbers, the capabilities, the hardware profile of the system, posts it back into Ironic, and now suddenly we've got megabytes and megabytes of JSON, which describe each of the nodes that are under Ironic's control at this point. So this is a useful thing. What do we do with this data? So we've been using this tool called Cardiff, Python Cardiff, which is about detecting anomalies. It runs through all of the JSON files for all of the nodes. It says, this node's an outlier. It hasn't got a RAID controller, or something else is wrong with it. Then you put that node into maintenance. You can look at it separately. It's a really, really valuable way of using Ironic to comb out all of the chaff that's in there, along with all of your compute nodes. Next stage, well, we build those images, the images on the previous slide. So we create a QCOW for our overcloud. This is then used for deployment. And I mean, this is really selling coal to Newcastle, isn't it? Because they're talking OOO. And here I am in HP, the guys who really pushed it into the world, or at least pushed it a long way into the world. But that's what we use. So OSP, Red Hat's OpenStack platform director, is built upon OOO, which in turn uses Heat and Puppet. A lot of the integration work that we've been doing has involved configuring OOO to deploy the OpenStack cloud and unpack it and configure it in a way which is oriented towards high-performance computing. So it unlocks all of these capabilities that we want. When that stops, we leave the OOO bit in its place because actually it is a right swine to work with, and I think perhaps that explains many other things about OOO's history. The next stage is to move on to, we use Ansible to build up the configuration from a baseline, And then we apply all of the site configurations, so all of our provider networks, all of the, the addresses and the usernames and the LDAP configuration, all gets applied using Ansible and a little bit of scripting, and then we, hey presto, from start to finish, we have built our cloud up. So that's obviously a very long and complicated process, and what we are doing is slightly off the beaten track of OpenStack deployments. So to mitigate the risks that are involved in that, we have three phases in the way that we develop things. We have the development system, which is really about exploring new HPC technologies, trying to get stuff working, trying to try things that are a little bit speculative. That's where I tend to spend most of my time. Then we move on to a staging system, which is like a miniature. It's like a model village of the production system. It's got HA. It's got 3 nodes of HA for the controllers. It uses the same nodes. It uses the same switches. It has some of the same storage. And really, that's about looking at how does the new things that are feeding in from development and the new things that are feeding in from Red Hat upstream in their product roadmap, how do those things join together, and do they actually work in a deployment? So we go from like a continual tight iteration on the development system to a periodic, occasional redeployment in the staging system. And then when things are happy there, we look at the production environment. So this is where users exist. We have service level agreements, or we certainly try to. And we really rarely touch this system. So we imagine upgrading this machine in place with as little disruption as possible. Periodically, for example, we will do the migration to OSP9 by staging it first, checking out that it runs with all of the extra bells and whistles that we put into our OOO config, and then deploying it to production as a scheduled piece of planned maintenance. So that's the machine in a potted version. Does it work? Yeah, it kind of does, actually. It is in its user adoption trials at the moment. It hasn't been easy to get to this point. I think we spent about 6 months in general building it up from being nothing to everything that it is today. We completed the deployment over the summer. It's in early trials. Now we're just getting the measure of this new system, and we're instrumenting it to understand the remaining weaknesses, the things that we have yet to fix. So far, the early user trials have found the performance certainly to be very strong indeed, and generally I think the feedback has been pretty positive. So that's good. So let's have a look at how it actually works for some of the different ways that people can use it. What can we actually do with flexible infrastructure? Well, some people like the idea of this flexible infrastructure in order to run workloads on it in the way that they're used to on the old systems, so they run Slurm. So it's cluster as a service. The nice thing here is that we can do things with the OpenStack cloud that we couldn't do previously in a Slurm workload environment. We've got three users here, 3 projects. They're completely separate from one another. They don't see each other on the login nodes. They don't see each other in the queues. They have a dedicated resource specially for them. It's sized to their needs, and it's deployed in a sort of an automated ballet of Ansible and other bits and bobs in order to create a Slurm cluster which is tailored to their configuration. That's really good. And when they've finished, they can unpack it or they can destroy the cluster. The resources get reclaimed, and then it goes back into someone else's usage. With a click of a button, we can do that. We can also deploy each of these clusters using a different software image. Now, let's say we're deploying, 197 projects, 42 research groups across the university. They don't all have the same interests in what software libraries they want to run. There are physicists, there are biologists, there might even be equine podiatrists, for all I know, medieval dentists is a classic. Each of those people is going to want to run a different environment. It's a real tension in a system where they're running bare metal HPC, where you have people who have different needs. Let's say someone needs to run one version of glibc versus another. They can't really do it very easily in the same workload environment in a traditional, conventional HPC cluster. So this is something that we can do trivially using the strengths of cloud. But it's only really useful, it's only really interesting if it actually delivers any performance as part of that. So our machine is virtualized, so we are running the NICs, running MPI over SR-IOV interfaces. And what we see is there's an overhead, as you might expect. It's about 5% in terms of the saturated bandwidth on the machine at the moment. I should stress, I mean, throughout all of the results we get at the moment, we've just deployed it. We're really just getting started with the idea of tuning it. So all of these results are delivered with no great effort to optimization. We just unpacked it and said, hey, it works, great. And that's what we get in terms of the performance. So actually, this is very faint, so apologies for that. More interesting perhaps for tightly coupled workloads is what's going on at the short end. So we're looking at message latency here instead of message bandwidth. We see about a 2.5 microsecond overhead for virtualizing the machine at the moment. Once again, that's going to come down when we start to look at things like pinning the virtual CPUs to the physical ones, a bit of NUMA awareness. All of these things are going to help bring that curve down, make it less erratic, generally lift the performance of the virtual environment. It will improve from here. This is a baseline. So that's one use case. We also have our data analytics. So the life sciences is very much more about high-performance data analytics. So we have all kinds of unusual workloads for HPC, non-traditional HPC, but very much traditional data analytics, all very familiar things. We want to be able to support those as well on our RDMA-centric OpenStack cloud. And we want to support them and make them perform as well as they possibly can too. Now, Hadoop's an interesting one, and Spark as well. You can actually get Hadoop and Spark ported to InfiniBand. That's something that we're looking at in the future. It's not part of this talk. A lot of these workloads don't fit the traditional HPC mold of Slurm and MPI. So a system that was built for MPI alone, well, there's no massive advantage to using OpenStack. So flexibility is what we're looking at here. These genomics pipelines are really data intensive. I mean, massively data intensive. That's why this system has so much storage, and that's why we have so much focus on data movement inside this machine. For these applications, we created a storage tier, a bit like, in the HPC world, they call it the burst buffer, but we have a sort of a cloud burst buffer, which is about providing this fast access to hot data. So we can prefetch data into our burst buffer and access it as in a disaggregated I/O from our VMs with very low latency, very high bandwidth, compared to the traditional approaches for solving that inside of cloud. So I was giving a lightning talk about it. These slides didn't turn up, but I'll quickly whistle through those. This is something we use RDMA, so that is an RDMA NIC from Colin at the back from Mellanox. I believe he's going to be taking cash today if you want a discount. We also have a very well-stacked Dell server with 24 SSDs in it. That is the essence of our burst buffer. We run Cinder iSCSI over RDMA using this machine. And this is the kind of performance difference you get when compared with running Cinder over TCP, which is the usual configuration, from the same hardware. So we took the hardware, we configured it for using RDMA, which is the top two, reads at the top, writes at the below, and then we flipped it over into TCP mode, ran the same tests again, and the bandwidth performance that you can see, well, we're getting over 5 gigabytes a second on our block I/O at the top there, and in the same in the TCP world, well, it's sort of, what is that, 1.5 or so if you're kind. Latency of I/O is also very important. It's probably more important. And what we can see here, this is a log scale on the y-axis. We can see we can gain a power of 10 in latency by using RDMA technologies in the cloud. So then finally, just to round off the results, this is the IOPS. So this is really looking at the throughput that this thing can sustain. And we clocked ours at just over sort of 550,000 IOPS for short I/O operations. Pretty good for a sort of a homemade machine. So compared to Ceph, actually, we've flipped over to the main presentation again. So this is from the development system. This is 6 SSDs instead of 24. So we peak at about 3 gigabytes a second. That's the red graph. That is essentially the same test that's running on the previous graphs. The green one is interesting, actually. That is the performance that's seen inside of the VM. So the red one is what we get over iSCSI into the hypervisor. The VM and the hypervisor between them somehow lose a ton of performance for short messages. That's really interesting to us. We're going to be investigating where that time is going. But having said that, it is still thrashing the pants off all of the other I/O systems that we have in our system. So the purple one is our Ceph performance. It's topping out just under a gigabyte a second for a single stream. And along the bottom of the axis is our Nexenta hardware, which I think is having a very bad day on this test. And they are very keen to understand why that is. So I/O latency from a virtualized environment. Well, the red one again is what we were getting into the hypervisor. We lose a power 10 going into the green line, which is the I/O latency in the virtual machine for the same hardware, for the same device. This is a very tricky graph, actually. If you've ever tried to get cumulative distribution percentiles to mean anything, when all of the data points are above 99, it's quite hard. So this is log scale at both the high end and down towards the low end, and then log scale on the Y. We had to use a real statistical shoehorn to get all of the data, all of the storage platforms onto one page. You can see there's several orders of magnitude difference in terms of I/O latency on this graph. And the purple one is our Ceph system. It's really not fair for us to compare it apples for apples with our hot storage system, because they're completely different in terms of what they deliver. The Ceph one offers massive capacity for a reasonable level of performance, but it also offers these very sort of enterprise level guarantees of data resilience, which we don't even pretend to offer with our hot storage. It's got RAID 10 on the system, but that's all. So really, it's not fair to compare them both in this way, and I will apologize to Ceph for that. Sorry. Right, so can you see that? It is not clear, is it? Sorry about that. It looked lovely on my screen. The work is not done yet with this system. What we're looking at here is TCP stream bandwidth. I mentioned that we have this dual network system. So we've got VXLAN for talking to the outside world through all the firewalls and the bridges and the other bits. And then we've got VLANs and SRIV for the east-west stuff inside. This is what the SRIV networking is approaching in terms of bandwidth. This is actually the bare metal performance inside the hypervisor. You can see that we get one stream performance of about 32, 33 gigabits a second. We get 10 stream performance, which is pushing the line rate of the system. On a 1500 MTU, that's about 48 gigabits. We're getting about 46. That's pretty good. We're pretty happy with that. We move to the VXLAN, and on the same reference, where is the data? It's actually 1.6 gigabits a second we're getting through our VXLAN network encapsulation onto the same 50 gig NIC. And this is testing it without any of the sort of neutron router or any of that bottleneck being in the way. This is from one VM to another across a VXLAN network. There's a problem here. I'm including this graph because it's something we're actively working on, understanding why that is. It's here as a cautionary tale that you might install OpenStack and it might all come up and kind of look like it works and, it pings. But you really do need to keep an eye on the technology and check that it's delivering on its promises in terms of performance. The more software and the more complexity that we add to these systems, the more chance we have of introducing something which is preventing our system from hooking up the kind of performance that it is truly capable of. And this is one of those examples. So this is a big problem for us at the moment for data ingest into our system, and some of our clients in the life sciences have very big data sets to load. We are working on that. Quite likely one of the reasons is this cool stuff. So I don't know if any of you have seen this. This is a project, a fairly new project from, I think Red Hat wrote it. It's called Skydive. And it's about visualizing that madness that's going on inside an OpenStack hypervisor or a controller node in terms of all of these software networking components. It just makes it just tells you what's, the leg bones joined to the thigh bone and all that. It just makes sense to string the whole thing together into one picture. And I think in our case, what's going on is that we've got 2 different NICs from 2 different vendors. We have 2 software bridges. The VXLAN is passing through all of these things, close to all of them. Somehow it's preventing the hardware offload from kicking in the effective way that it should be. So that's a problem. We're working on a solution. Our partners in Red Hat and Mellanox are being very helpful with understanding that. So what can you do when it's not looking good? This is an interesting thing. So OpenStack is, obviously it's open, it's very friendly, there's a big community out there. And sometimes the open bit is really, really vital for when the stack bit is not so good. And we joined the community, so part of our purpose in Stack HPC is really about bringing together this community, helping to reinforce it, make a self-sustaining thing. So we go out to the community and find answers to our problems. This year, we created, with the OpenStack Foundation, a working group specifically focusing on scientific compute, research computing use cases. Already we've got dozens of people, dozens of institutions who are involved in this from across the world. That OmniPath network from the top at Bridges, those guys are in it. They're really active. They're very helpful. A number of other institutions deploying very similar systems to ours based on Mellanox, Red Hat, RDO, anything really. There's a real breadth and depth to this working group. It's a very helpful resource. We share information about what works and what doesn't. I'm a co-founder and currently co-chair of that working group. Together, we're making a big impact. It's just a fantastic thing. So if you're in research computing, I'd really like you to join in too. So can we really do it? Can we really deliver this idea of OpenStack in research computing, the software-defined supercomputer, which is, I'm sorry, a little bit pretentious. With OpenStack, I really think we can do it. I might even say that without OpenStack, I'm not sure that we could do it. Already we've managed far more than we really expected to with our project at Cambridge. We've got a great opportunity looking forward from here to deliver something more special. So rather than recreate what's gone before, we have the opportunity to exploit all of these things that are going on in terms of cloud-native HPC, building on the innovation that's coming in from software-defined infrastructure. But I really think that it's something that we have to do together. And I think we have to do it openly if we're all going to get to the same place in the same time. At Cambridge, there are already exciting new projects being kicked off that take these concepts, the kind of stuff we were just talking about, really to the next level in terms of accessing high-performance data, using software-defined infrastructure and the innovation that brings in, but also bringing in the efficiencies, the scalability, and the performance that the protocols in HPC have been honed and iterated and refined and improved over the decades. Down the line, I'd love to come back and talk about those, but first we have to do it. A lot's happening in OpenStack that is going to sustain this as the driving force for modern scientific compute. And by no means are we the only ones, the team at Cambridge and at Stack HPC, who see this phenomenon. You might recognize this guy. So this was from the OpenStack keynote in Austin. And Jonathan Bryce talked about how research computing and big data is a real thing in the OpenStack ecosystem. It's a really important thing. And through things like the Scientific Working Group, we are working to keep that prominence and make sure that the use case for research computing is well advocated. And he even cited our project at the University of Cambridge as an example, which, well, isn't that nice? I was very happy about that. So let's continue this discussion on the value of community. I suggest we all go for a beer and make some commits to Nova. Thanks very much. Eric.
Have you measured barrier latency and how it scales across the machine?
No, we haven't measured barrier latency. Barrier latency is that classic kind of problem that you're talking about, exascale kind of issues. No, we haven't measured barrier latency. I think it's worth pointing out we have 80 compute nodes, and it's really not the kind of scale where those kind of problems like MPI barriers are going to dominate. I mean, that's the kind of problem that Cray is facing, and I'm sure they've got interesting solutions which they'd love to talk to you about, but, well, it's using an Intel network anyway, so you probably know better than them. Pierre.
In your diagram with the 3 HPC clusters that were virtualized, I noticed that they lined up to be on separate compute nodes. Was that just so that the figure looks nice, or do you actually have configuration of flavors and the Nova scheduler to make sure that each tenant is physically separated on the infrastructure?
Okay, so the question was, do we segregate our workloads and our clusters onto different hypervisors? Pierre, I would say that that was more of a coincidence, and it's more aesthetic than due to any particular policy that we have in place at the moment. So at the moment, we don't place any kind of segregation to a hypervisor, and I think that it's the sort of thing that might come along down the line, but we'd have to understand a little bit more about the impact that we have in our system of the sort of the noisy neighbor problem in an HPC context in order to make those kinds of calls. And we're just gathering data at the moment. I mean, you can see the stage we're at with things like networking. So we need to walk before we can run on those kinds of refinements. But yeah, it's a good question. Hello.
Are you guys dealing with a problem where VMs are sitting there doing nothing, just sitting idle yet?
There are a lot of VMs that are sitting there doing nothing and idle at the moment. I wouldn't say that we have had the problem of that being sort of consuming too much resource. The level of utilization in the system is something that is bothering me, for sure. So, I mean, if you look at a conventional HPC environment, for all its restrictiveness, it really packs it in terms of the amount of compute resource used. The level of utilization will be very, very close to saturation. In a cloud environment where people, you know, they'll start a VM, it's consuming some resource, and then they'll go home for the night, and, you know, it's not actually doing anything.
Or worse,
that,
gone off on holiday for 3 months.
You're absolutely right. And in fact, you've just reminded me, when I finished working at Cray last year, so just over a year ago, I left 4 or 5 VMs running on their system. So good case in point. I don't think we've come to that problem yet. I mean, certainly the team who work in Cambridge on the research computing platforms are very hot on managing their resource effectively. They get very good results. So, for example, they're very good at policing the usage of the Lustre file systems to prevent people from leaving large piles of files on there, because that becomes a problem for Lustre. So this is the kind of thing that we're going to be looking at, but it is really too early for us to say whether we're going to be doing it now or soon or never. Daryl.
So what allocation ratios are you using for CPU and RAM?
Right now for HPC it's 1-to-1. So I think that we are looking at supporting sort of institutional services as well, because, you know, that's what OpenStack can do. It's very flexible. And those would be heavily oversubscribed for things like web servers and wikis and whatever else, the other web platforms that are going on in the beige boxes upstairs. So, but at the moment, all of the HPC stuff is 1-to-1, and I think we will pin them to vCPUs to physical CPUs as well. So, sorry, yes.
If you're in the resource management within the virtual clusters with Slurm, are you using something like Slurm to manage the deployment of the virtual clusters or anything like that?
Okay, so the question was Slurm and OpenStack, which is the cart and which is the horse, I guess, isn't it? Well,
Yeah. What's managing the instances of the virtual clusters?
so there are some interesting things about this. When you look out across the ways that people are approaching integrating cluster as a service onto an OpenStack environment, people have actually taken both of those approaches. There are people, Ohio State University, for example, they've done some interesting work with virtualized MPI and using Slurm for supporting those environments. What they do is they boot a VM to run the workload, and then they kill the VM at the end of the workload. I don't think we're going to do that, because if we take that approach, then anyone who's running a stream of smallish sort of workloads is really going to put a lot of stress on the OpenStack control plane in terms of booting the VMs all the time continually. You know, there'll be this process. It will also add a lot of impact in terms of the startup time for the job, certainly frustrating, and it also adds impact in terms of the overall utilization of the system, because booting time is really dead time. So I think we are going to go for the alternative route where we boot a partition, the image is deployed with Slurm inside it, Slurm pops up and manages the nodes. And I think that approach makes a lot more sense from OpenStack's point of view. And also it probably makes more sense from Slurm's point of view as well. The other side of the issue with using Slurm to create virtual machines is that you never really know how much resource is available to Slurm, because, of course, there's another scheduler involved in OpenStack. There's Nova saying, well, I'm going to just deploy another 1 million virtual machines over here. And then Slurm thinks, well, I'm going to deploy another 1 million, and those things. And the point where Slurm comes to execute the workload is after the point where it checks whether it's got the resources available. So you check it's available, someone else grabs all the nodes, and then you try and launch the workload, and then you can't create the virtual machines, and you're kind of stuck. So we're going to go with the former one and have Slurm running inside of, hosted inside an OpenStack environment. That isn't to say that you can't do interesting things, though, to do with getting Slurm to talk to OpenStack services. There's some very interesting work going on at Los Alamos, for example, to do with delivering Docker images that are run inside of Slurm, and those are downloaded from OpenStack Glance. Those guys are building on that to integrate Slurm with Neutron so that you can run a virtual tenant network for your workload instead of having all of the workloads inside your Slurm partition sharing essentially a flat network inside of OpenStack. Okay.
Excellent. Right.
Thank you. Beer o'clock.